Hello everyone, my name is Dmitry Duplyakin, and I'm here presenting the work my colleagues and I did on taming performance variability. This work is done by folks from University of Utah and University of California, Santa Cruz. Fun fact here, both Carl Smeltson and I were at CU Boulder for our PhDs at different times, and I would have personally liked to be at RMACC at Boulder presenting this, but I can't be there due to conflicts, and I'm thankful that the organizers allowed us to record this video. All right, in terms of the structure, I will first talk about the work we presented at Usenix OSDI last year. There was also recent related talk at CPS IoT Bench Week, and I'm using some slides from that talk. And at the end, I will talk about our current and future efforts. All right. In terms of the high-level goal in this project, we wanted to run a large-scale, long-term analysis of hardware performance, where we pay special attention to performance variability, looking into variability trends and anomalies, and trying to understand how the variability shows up on an individual machine with repeated runs across different types of machines, and also on a set of diverse benchmarks. In this work, we posed several specific questions, and we wanted to understand, assess the level of confidence that we can have when we work with performance results. We wanted to have a systematic way of figuring out how many experiments we need to run, how many measurements we need to collect for individual benchmarks. And on the facility side, we ran this analysis. We gathered performance data from the Cloud Lab facility. I'll talk about it in a minute. And on Cloud Lab, we wanted to look at the facility perspective, where facility needs to provide to the users most sort of reliable, most representative machines. And we wanted to kind of look into that and find ways the facility can do it. All right. Running things, so we ran our tests on the Cloud Lab machines. We ran each benchmark on each machine periodically over a long period of time, and we also did this across a diverse set of machines. We ran memory, disk, and network tests, although since this publication we've added some CPU tests. And at the moment of publication, we looked at about 11 months of performance results, over 800,000 data points collected on over 800 machines. All right, Cloud Lab. I would encourage you to look at it. Look at cloudlab.us if you're not familiar with the facility. Just briefly, it's a distributed facility for cloud computing research and education. This number here is fairly old at this point. It's about 2,200 servers deployed at 3 sites: University of Utah, University of Wisconsin, and Clemson. When we ran this analysis, we cared about exclusive raw access. So there's no sharing, there's no over-provisioning, there's no virtualization. We get on these bare metal machines, run our tests, and then release them so other users can use them. In terms of different configurations that we studied, we looked at many different combinations of hardware types and workloads and their parameters. I'll talk about that in a second. All right, let's talk about confidence. Here I'm going to present a set of slides where I show coefficient of variance, which is standard deviation over the mean expressed in percent. And I'll show those coefficients for 70 specific configurations we studied for disk, memory, and network results. On the lower end, we have network bandwidth tests, where results are really consistent, show very low variance, and the coefficient of variance is below 1%. After that, we have a mix of disk and memory tests, where things are like the results are fairly stable, and we see the variance of about 4%. After that, we have a set of noisier tests where we can see up to about 15% variation. And on the higher end, on the high end, we have network latency tests, which I suppose we should have expected. The latency numbers are really low, and even a small variation can cause sort of high coefficient of variance here. Here we can see up to about 30% variation. When going from that high-level macro perspective and getting into more of a micro analysis, so to speak, we used confidence intervals. As a general rule of thumb, the confidence intervals shrink as we get more measurements, and this plot shows that. This is an example of that. This shaded area shrinks as we keep running our experiment over and over again, and we can see that past a certain number of experiments, for example, I would say 200 or 300 measurements, after that we don't see a significant change in the confidence intervals. It means we really got enough data, and additional measurements won't really impact the confidence intervals. It is well known from the literature that it's a good idea to test our distributions for normality, and specifically in the performance analysis context, the assumption of normality doesn't hold in most of the cases. And here we use what's called Shapiro-Wilk test with 95% confidence, and this testing confirms that statement. Here we have some results. Out of 713 configurations that we studied here, 710 of them are actually not normal, and we can't use the sort of the summaries and inference that is correct for Gaussian distributions. As a sort of approach to address this, we use what's called non-parametric statistics, and those tests don't rely on the assumption of normality. Here's a little summary of what I've just said. Essentially, we need to repeat our experiments. We need to keep collecting more measurements. The more we do it, the more confident we can be about our findings. Equipped with the statistical perspectives and insights that I've just shared, we're going to look at how many experiments we need to run for each configuration to get the desired level of confidence. For this goal, we build a system or a service called Confirm, or a confidence-based repetition meter. It is a tool that is specific to Cloud Lab, since it uses Cloud Lab performance data, but the analysis that it implements is general enough that it can be applied to any other system, cluster, cloud, HPC facility, or whatnot. Essentially, as long as a system produces data that includes measurements from different machines that can be compared, from different classes of machines that we can compare with the timestamps and the well-marked performance results. Then we can sort of go through dissecting that data in a confirm-like way. Okay, I'll walk you through how it works. We look at sort of partial sets from the data points that we have access to, and as we vary the number of runs, we track the medians, the sample medians. Specifically here we use medians instead of means because medians are better aligned with the non-parametric statistics that we use. At the same time, we track how confidence intervals change. They shrink, as we've talked about it. And then what we do here, we try to sort of cap these confidence intervals and look for the moment when the confidence intervals fall within certain bounds. For example, we can choose fairly tight 1% bounds shown here with the dashed lines, and then confirm helps us to see the point where we sort of we satisfy this target. In this particular case, we would need about 33 measurements or runs to get into that range. We use confirm to look at a number of different configurations, and there are a couple shown here on the slide. We look at sort of the relationship between the coefficient of variance, which is pretty easy to estimate, and this recommendation for the number of runs, which confirm produces, which is a lot it's a estimate that requires more computational work. And we see some results here. Very brief summary here. The higher the coefficient of variance, the more runs we need to get, need to perform. At the high end, we get into this 600 range where we need 600 measurements for this configuration with 8% coefficient of variance. And in the middle, our recommendation would be to really look at both, get the coefficient of variance first, but then still run confirm, because these recommendations vary quite a bit even for the configurations that have similar coefficient of variance. Essentially, these two metrics are related, but they treat the outliers in the performance data differently and kind of react to it differently. After this little summary, I'm going to actually switch gears and do a little demo of confirm. Here it is. Confirm runs at confirm.fyi. It's publicly available, and you can check it out if you want to after my talk. So for this quick visual, we're going to look at disk results, and this plot here shows how many measurements we get every day over the last almost 2-year period. Sometimes we get nothing, like in this gap. Either our collector was down or the system was fully utilized. And on the other end, we get sometimes up to about 1,500 measurements each day. We're going to look at one of the clusters. We'll choose Utah hardware. We're going to look at XL170s. These nodes are the most recently deployed in Utah cluster. Each of those nodes has this device. So we're going to run the benchmark against the raw device and skip the file system. We're going to do the write testing with the high I/O depth. That's our configuration here, the hardware plus the specific workload. These are the nodes that are available within this hardware type. We're going to choose all of them. And at that point, we're looking at about 2,000 measurements that we've collected. Confirm will run through them, present the statistics and the confidence-based recommendations in just about a couple of seconds. it does take longer for a larger data set. All right, well, with these disks, we clearly see some bimodal distribution in this test. We have sort of this lower level of performance at 340 megabytes a second, in contrast with the higher value at about 380 megabytes per second, and some measurements in between. This is what we get, like, if we track kind of our progress in terms of how the medians and quantiles changed as we collected this data set. These are individual estimates, like node-specific estimates for medians and their confidence intervals. And then this is the kind of the key component of conform analysis. This plot here, it's going to update in a second. This what gives us a sense of how many experiments we need to run. And as we can see, there's sort of this downward trend in the median here. It's coming from the fact that this lower performance in this bimodal distribution, I'm going back here to this plot, so it turns out there are more of these points with lower performance than the points with the higher performance, and because of that, the trend is sort of down facing, and it's clear that we can't even get to the point of 1% CI bounds using 2,000, almost 2,000 measurements. If we switch to 5% confidence bounds, then we can I think get to that level fairly quickly. Yeah, that should be feasible in this configuration. All right, yeah, for that it's still a non-trivial amount of work. We still need to run almost 160 measurements, but that is a doable task. All right, that's confirmed. That's a quick demo. You can explore other configurations and settings if you'd like. I'm gonna go back to the slides here. All right, this set of slides talk about the ways the facility can respond to the variability and in certain cases remove the outlier nodes, the nodes that produce results that are different than the results produced on other nodes, on other comparable nodes. I will actually go ahead and skip this part of the talk in order to stay on time and actually try to finish early than go over, but I would encourage you to look at the findings and the techniques we described in the paper. I will flip through these very quickly and only make one comment at the end of these slides. My comment here is that there is a statistical technique that we've used here. It's called two-sample kernel test. It's a non-parametric test, which is powerful and sophisticated, and it can help us compare distributions and use this comparison to sort out the servers that produce abnormal results. And we can tune it in a way that this test responds to not to the infrequent outliers, but rather to the frequent outliers, the ones that contribute to the bimodality or a strong skew. And so if a server, in other words, if a server once in a while produces a abnormal result, that's fine. That shouldn't really discredit this particular machine in any way. But if it produces those abnormal results pretty frequently, more than other machines, then something needs to well, certainly that node needs additional analysis or potential admin attention. And so I'm not going to go into further detail on this here. There's tons of related work in various niches of performance analysis, and we've got some papers referenced here and obviously more in the paper. As a summary here, I'll just point out that we were running this analysis, we were trying to use the best practices sort of recommended in the literature and use our own sort of high standards for what's reliable, what's sort of conclusive, and we're trying to really kind of go beyond just providing the summaries. We wanted to understand like how consistent they are, how reliable they are, how they change over time, and so on. In these tasks, we heavily used confirm, and we find the analysis implemented in confirm to be powerful and applicable to many other environments. Again, more lessons that we've learned for that, please refer to the OSDI paper. Current efforts, we've got tons of new ideas and kind of interesting sort of techniques we're exploring. We've seen a version of this slide that relates to the OSDI paper, but now we've got a lot more data. It's about 4 million measurements that we can look at from over 2,000 servers. We added the CPU tests where we run the NASA Parallel Benchmark Suite, NPB, and we as part of that we run integer sort tests and also floating point tests like FFT, LU, multigrid, and many other numerical tests. This is a breakdown of sort of the overall number of measurements that we have, and then this slide shows the categorization in terms of the type of measurements. So memory is what we've studied the most. We've got over 2.7 million measurements for memory tests, and on the right side here we've got network tests that are sort of slow burning, but even for those tests we've got a fair number of measurements to run powerful statistical tests. We see quite a bit of variation in the results coming from the CPU benchmarks. In fact, this was really surprising. Going into this project, we thought that for sure disk and network and memory to some extent would show the higher variance, but we see one example here where the coefficient of variance is just through the roof. It's 150%, and we see lots of big outliers here. In this particular test, we usually complete under 10 seconds, but occasionally the same test runs over 100 seconds. We explore correlations between individual tests, and the goal here, and it's not complete by any means, we're exploring it, we've got some thoughts on this, but there's still work that needs to be done in order for us to reduce the overall number of tests that we run. In other words, we don't need to really go in depth and run various configurations within, for example, within the set of CPU tests. Maybe we can reduce that set over time and then only run the ones that are most representative or the ones that differ from each other the most. And again, another room for optimization here is figure out where memory tests correlate strongly with the CPU tests and sort of reduce the overall set based on the correlations. We look at performance tails and focus more on the tails now as well. We used to primarily look at the medians, which is this line and shaded area in the middle, but again in analysis of latency or bandwidth and even CPU performance, we sometimes care about sort of the worst case scenario, the best case scenario. For that, we've expanded confirm to add this perspective. We'll look at stationarity and learn quite a bit again from this different approach where we treat the data as the time series data, and we can reason about stationarity and then using specific stationarity tests. All right, future work. We've identified a couple of ideas for complementary and additional analysis. And among these, I want to focus the most on the last one. Clearly, we've done a fair amount of work on Cloud Lab, and at this point, by now we've seen a lot of surprising stuff in this analysis, but we understand the hardware performance on Cloud Lab pretty well. We understand its trends and anomalies. And now we want to branch out and see if we can apply this analysis to other facilities, other test beds, clouds, and potentially HPC facilities. And we're hoping that people in the audience here find our work interesting and potentially complementary to their work, and maybe we can talk more, exchange notes, and potentially collaborate. So if that's the case, if you have that interest, please let us know. Here's a list of techniques that we've used. There's certainly a lot more we can do, but this was already a good set for this analysis. Confirm.fyi. Please explore it if you'd like. And here's my last slide. Here I want to thank you for your attention. Again, questions and comments, including the ones about collaborating or exchanging notes on this and running more benchmarks, please send those notes to this email. And I would like to give credit to my colleagues and collaborators who worked on this project. With that note, thank you for your attention and have a good day.